All right, well, get your slides out. We're going to talk about boiling point and melting point and solubility of different functional groups. So in front of you, there's a chart of a homologous series of alkanes, which means they are one carbon added to the end of each chain as we go across, and nothing else is changing. So we're not changing the structure, they're all straight chain. We're not changing and adding any functional groups or anything like that. These are all just methane, ethane, propane, butane. The only addition is that carbon, and with it 2 extra hydrogens added to the end of each chain. And if we look at the pattern of boiling points, it starts at negative 67 degrees Celsius, goes to negative 88, negative 42, negative 0.5, then we're into the positive 36, 68, 98, 125, 150, and finally 174 degrees Celsius. This is a fairly consistent pattern of increasing boiling point based only on the addition of the carbon and 2 hydrogens to the end of the chain. This is 2 reasons. 1, to boil something, what you're doing is changing it from liquid to gas. So you're increasing the energy that that molecule has. If you remember from grade 11, my liquids were like this, where they're held together by intermolecular forces, and gases are like this. Okay? There's no intermolecular forces holding those molecules together. So when you add that additional CH2 to each carbon chain, you're adding weight, and it takes more energy to move heavier things. That's a fact. That's a fact for molecules as well. It takes more energy to move heavier things. But you're also adding more electrons. Every carbon and hydrogen contains electrons that are added to this chain. More electrons means there's a greater surface area. And a greater surface area means there's more interaction for London dispersion forces. Because London dispersion forces are that instantaneous dipole caused by electrons going over to one side of the molecule and having that very slight partial negative charge on one side. Well, if you have more electrons, then you're going to have more surface area for London dispersion forces to occur, and thus we have an increasing boiling point based on increasing mass and increasing electrons in the molecule. As we keep going, something that does decrease is branching, because it decreases the area of contact between molecules. If you think of 2 straight chain molecules, they could kind of lie right on top of each other, or if they're longer, there's a lot of area there. But as you branch off from that molecule, it becomes more rigid and harder to find the surface area to bond, because there are branches sticking out of those central carbons. So you don't have the electrons from the carbons in the center contributing to the London dispersion forces. So you can look at 2 alkanes with the same molecular weight. The more highly branched one is going to have a lower boiling point. Okay, so weight and surface area for London dispersion forces play a part in boiling points. Pentane has a boiling point of 36.1 degrees Celsius. 2-methylbutane, 27.9, so we're jumping down about 9 degrees Celsius, and then 2,2-dimethylpropane, jumping all the way down to 9.5 degrees Celsius. It takes less energy to boil this more highly substituted, highly branched molecule, even though for all of these, their chemical formula is the same. They are all isomers of pentane. They are all C5H12. There are no double bonds. We haven't removed any mass. They have the same molecular mass. They're all isomers, but just the branching changes that boiling point. The functional groups will also change the boiling point. if you add alcohols to your chain, you've added an oxygen that is highly electronegative. So now there's potential for polarity, which leads to stronger intermolecular forces, whether they be dipole-dipole or hydrogen bonding. Both of those will increase the strength of the molecule, and thus you require more energy to break it apart. Amines are the same way, because nitrogen, again, is going to add more weight to the molecule, but the nitrogen has a lone pair of electrons on a highly electronegative center, and you could have dipole-dipole moments or hydrogen bonding occur. If we're looking at and comparing the classification of amines, a primary amine, because that nitrogen is right on the end, is going to have a higher boiling point than a secondary or a tertiary amine. This is because the nitrogen on the end would, in a primary amine, is having one nitrogen carbon bond and two nitrogen hydrogen bonds. And what we know about nitrogen hydrogen bonds is that is 1/2 of the requirement for a hydrogen bond. They would then have to bond to the lone pair of electrons on the nitrogen of another amine, and there are two locations for that hydrogen bond to occur. You move it to be secondary, there's only one nitrogen hydrogen bond, and this drops from 97 to 84, so it drops a whole 13 degrees Celsius. If you make it tertiary, you no longer have hydrogen bonding that can occur, and this tertiary amine would drop from 84 to 65, a much bigger drop than in the primary amine. I think I now have some examples. We're going to skip through a couple of these, and that's how we'll start the next class for each of us with those. So, melting points follow a very similar pattern than boiling points. As the molecular mass increases, so does the melting point. The increase in the melting point is less uniform, less regular. If you look back at that chart, you almost increased by like 30 degrees Celsius each time for boiling point. It's more rickety for melting point because of a concept called packing. And packing is something we're going to explore in this second unit. So it's a property that determines how well it packs together as a solid. Since melting is changing from solid to liquid, how well the solid is packed together would affect the amount of energy required to unpack it. But we're going to look at the different shapes of packing, like these guys, in the second unit. So going back to this chart, you can see the melting point is not as uniform. It doesn't increase as consistently. Here it actually goes down, but then it's 87, 38, 29, 95, 90, 56, 53, 29. It kind of increases by a small amount and then a larger amount, then a small amount and then a larger amount. And that is because of the even and odd numbers of carbons in the chain. What you should note from this slide is it still does increase with molecular weight. That is still true. It's just a small amount, then a large amount, then a small amount, then a large amount. So here we have a chart showing that, and the odd numbers kind of increase in their consistent curve, and then the even numbers as well. But if this is a 1 carbon, methyl, ethyl, propyl actually goes down, large jump to butyl, small jump to pentyl, large jump to hexyl, small jump to heptyl, and then you keep going up like that. So it's still increasing with molecular weight, but it is not as consistent. Solubility. All right, we talked about this in grade 11. Like dissolves like was something that we used to remember what was soluble. And what it means is something that's polar will dissolve in a polar solvent, and something that is nonpolar will dissolve in a nonpolar solvent. That's what that says there. So molecules with similar intermolecular forces will be able to mix freely. Okay? This like dissolves like can be more grade 12-ly defined as similar intermolecular forces will mix more freely. Water we call the universal solvent because of its ability to dissolve many different solutes. So let's look at an ionic solute with a polar solvent like water. The positive and negative ions from those crystals can be surrounded by the partial positive and partial negative ends of water, and thus an ionic solute will dissolve in a polar solvent. An ionic solute with a non-polar solvent does not dissolve very well. Think of this as an ionic solute being a bunch of marbles that are magnetic, and a non-polar solvent being a bunch of marbles that aren't magnetic. You throw them all into a large tin of some sort, and you shake up the tin. Eventually, all of the magnets will stick together, and all the non-magnets will just kind of be around the magnets. You have nothing in the non-polar solvent that is able to surround the positive and negative charges, so the positive and negative charges hold themselves together. But if you had a non-polar solute and a non-polar solvent, then none of them have a charge, and they are able to surround the molecule and dissolve. So a lot of organic solvents like diethyl ether or benzene are used for dissolving non-polar solutes. So here you have water not dissolving with a non-polar solute for the same reason. This is like the oil and water connection. Because there are no charges or on the ends of this non-polar solid, the water will not be able to dissolve it. Most organic molecules are usually soluble in organic solvents such as diethyl ether and some of the other ones listed there. Diethyl ether, dichloromethane, hexane, those are common organic solutes. However, some molecules will be soluble in water, and because water is the universal solvent, we're going to be looking at this interaction a bunch.